All right, Chapter 7, Section 2, Properties of Parallelograms. This is day 2 of 2. We're going to start with a proof problem regarding parallelograms and their properties. And so this is the situation we're basically given. Okay, now before we jump too deep into this problem, I just want to talk about proofs in general at this point. A proof is essentially a puzzle. Okay, and if any of you are fans of puzzles, you're intrigued by them and stuff, that's essentially a mathematical process of breaking down a puzzle because there are proofs and reasoning along the way. And so in this case, we basically have to connect the dots or complete the puzzle to reach a finish line, to accomplish a goal. In this case, we're beginning with this diagram, and we're being asked to prove, based on the information that we're given, the following results. And there is not something that is like a rule or a theorem that automatically lets me jump to this finish line. So there is a bit of a process, a bit of an investigation and connecting of dots. It will take a couple of steps. It won't take many steps in this case. And some comforting thoughts here is that, particularly in these early on geometry units that you have in math in high school, you'll tend to be given things that can be proven in a half dozen steps or less, as opposed to a college classroom for those that end up pursuing this long term, where you can have proofs that are upwards of 20, 30, 50 steps or longer. Okay. In this case, this one will be a 4-step problem, and it'll be fairly basic. Okay. So I will jump back to the actual wording and format of what you will see as far as a 2-column proof goes. I just wanted to start with like a nice zoomed in version of our situation, our diagram, our question, and what we're being asked to prove here on the whiteboard. Okay, so what we are given. We are given 2 4-sided figures that seem to be connected by a point D here in the middle. Okay, we have these 2 quadrilaterals, 2 4-sided figures, and because of these arrows, we know we're dealing with parallelograms. The fact that in this quadrilateral over here on the left, this larger one in ABCD, opposite sides are parallel to one another. That forces this to be a parallelogram. In the smaller one, I forgot to write F over there. F is this guy all the way over here on the edge in that corner. But GDEF over here on the right-hand side, the smaller quadrilateral, again, opposite sides are parallel to one another. That forces this to also be a parallelogram. And why does that matter? Okay, as soon as we know these are parallelograms, we can immediately apply and associate the 4 theorems that we talked about in the first day of this notes. Okay, so in yesterday's video, you'll recall that we went over 4 different theorems. The first of which said that within a parallelogram, like say for instance this guy, within a parallelogram, opposite sides must be congruent. So if I were to measure the length from C to D and then from B to A, I should get the same distance, just as I should get the same distance from A to D as with B to C. Okay, that was the first one, and the same thing would apply over here. And the second theorem we talked about was opposite angles on the inside of a parallelogram are also congruent. So for instance, angle C up here, whatever this measures in between here, has to match and be the same as angle A down here. The same would go for angle B over here on the left and angle CDA, this guy inside here. Okay, so that was the second theorem. The third theorem had to do with consecutive angles. So for instance, angle B and angle A are both consecutive angles. Whatever measurement was here would have to be supplementary or add up to 180 degrees with whatever was down there, just like it would have to match or be supplementary with angle C up top. And then the fourth theorem had to do with diagonals. Now they're not drawn here, but if I were to connect point C down to point A, I would create a diagonal in this larger parallelogram. Just if I were to connect B to D, I would create the second diagonal. And the rule about parallelograms was that these diagonals have to bisect one another. In other words, they would chop each other in half. Or another way to think about it is that if I were to draw these diagonals, they would perfectly meet at each other's midpoints. Okay, and we'll actually deal with that in one of our coordinate grid problems in just a bit. Okay, so again, the emphasis that I want to make there was that because we know these each are parallelograms, all of those theorems will immediately apply to each of these figures. and that will be useful for what we're being asked to prove. Okay, the next thing to just kind of be aware of here, and it's actually going to be a little bit, it will be used in this problem, has to do with the fact that these two figures, these two quadrilaterals, share a point at point D. And not only that they share a point there, they also appear to be kind of sharing a line segment, two line segments, in fact, that they're basically extensions off one another. That will become important for one of the inferences that we make to a little bit of an older theorem, but one that will apply here. Okay, so again, one of the important things that we're going to see with this diagram is the fact that these two segments are continuations. In other words, they make an X right here, right? So what we're being asked to prove here will help dictate which of these theorems we end up using. Because what we're being asked to prove here is that angle B, this guy over here, has to match or be congruent to angle F all the way over here on the right. Now, it's a little bit of a challenge in this case because there is no individual rule that will make us immediately jump to that conclusion. And the reason why is because these angles are separated into two separate quadrilaterals. They're both parallelograms, yes, but they're completely different shapes, okay? Maybe not completely, that's probably an exaggeration. But what I'm getting at is that they're not within the same parallelogram. So there is going to be that we will have to find a way to connect the dots that will somehow relate this figure to this one over here. And it will have to do with these shared elements. Okay, so what we're being asked to prove is that we want to find a way to connect these two angles. So these two angles, because we're talking about angles here, we can immediately kind of ignore certain properties, namely opposite sides being congruent. The side length from B to A doesn't do me any favors or help me with any information in regards to an actual angle measurement, at least not yet. We haven't gotten into trigonometry yet. Okay, but within this figure, the one that will be most helpful is what's called the opposite angles theorem. The opposite angles theorem. That was the second theorem that we talked about yesterday. So let's break that down. The opposite angles theorem says this: within a given parallelogram, angles that are diagonal or opposite one another will have to be congruent or match. Whatever measurement has to be the same as the other. Now, why would that be helpful here? Again, if I'm trying to show some connection between B and F, which are in two different parallelograms, I might care about specifically, well, maybe what do these measure if I can find a way that they measure the same thing. So one way I can do that is by looking at angle B here, and based on the opposite angles theorem, I know that this angle has to match or be congruent to this angle right here, because that's the angle that's opposite or diagonal to it. So angle B and angle CDA, this guy right here, this little wedge, these two have to be the same measurement. Why? Because this is a parallelogram. Now, for the record, angle C and angle A also have to be congruent. They're just, I don't need that information right here because I'm really focusing on angle B and finding a way to connect all the way here to angle F. All right, well, some of you may have seen this, but I'm also dealing with the second parallelogram here. So let me deal with the opposite angle theorem in that one as well. Again, trying to focus on a way to connect the dots between these two guys. I want to find a way to connect F to B over here. So I'm going to care about what F measures. Well, for right now, I'll go ahead and put double arches. I will be able to ultimately show that they are going to be exactly the same over here, but let me go ahead and use a different color and different arches just so we can kind of think of them as two separate figures to start with. So again, according to opposite angles theorem, angle EDG, this guy right here, has to match or be congruent to angle F over here in this corner. Okay, so that's our opposite angles theorem. And again, we can apply that immediately because we're dealing with a parallelogram. Okay, at this point, the way that we can connect dots between one figure to the other, we're actually going to be referencing a bit of an older theorem that you will have come across in Math 1, or at least an earlier algebra or geometry class. And the theorem is called vertical angles. Vertical angles. So what are vertical angles? Basically, anytime you have an intersection of two lines or two line segments, like we do right here, anytime you create that X, right? You've essentially created 4 angles. And we can count them right here, right? Working around this intersection, you've created 4 angles. And because they are continuous lines or line segments that pass through that intersection, the rule is that angles that are opposite each other, so for instance, top and bottom here, have to be congruent to one another. And these left-right ones have to be congruent to one another. This will ultimately be how we connect one of these parallelograms to the other. So again, because of vertical angles, the idea that anytime I have a continuous line or line segment intersection, I create a pair of vertical angles. These angles right here have to match CDA on the left and EDG on the right. So in this case, let me go ahead and go back to green. If this angle is the same as that, I can actually erase this little 2-arch guy right here. And I know that it has to be equivalent, match, or be congruent to angle CDA on the left. And that's good because now I've immediately connected this angle here to B. So I'm one step closer. And the last thing should be a little bit easier to see at this point. And that's that within this parallelogram now, whatever angle measurement this is has to match whatever is here. So the fact that this is now a green arch, that it happens to match these two, the fact that it matches these two doesn't matter at this point. This guy has to match this one. So now I can get rid of these blue arches. And now here's where I will ultimately get my continuity of 4 of the same angle. And so we've officially been able to prove this statement. And here's how. Angle B, since it matches angle CDA right here, these two have to be the same. And because of vertical angles, these two have to be the same. And then again, using that same exact theorem that we did in this left one, opposite angles here have to be the same. This is essentially a form of something called the transitive property. The transitive property is the one that you will recognize when you hear it. It's the one that says, if A equals B and B equals C, then A must also equal C. It's a way to connect the dots between a few seemingly separate things, separate objects, in this case, angles. Okay, so even though these two were congruent, that also meant since these two guys were the same, that this guy also had to match this one. And because these two guys were the same, I could immediately connect this guy all the way over here. Okay, so that was a lot of wording, a lot of description to get to that point. Many of you probably saw that in a couple steps before maybe I got to it. But we'll be able to show this and break this down in a pretty efficient way, and we'll get it done in 4 moves. 4 moves, okay? So let me jump to what the actual structure of the 2-column proof will look like. I'll talk about that for a minute, and then we'll wrap up this problem with what would actually be written down in the answer form. Okay, so jumping to our notes, down here on the bottom of the first page is where we have our 2-column proof. So just a couple of words really quickly about how a 2-column proof is organized. What is a 2-column proof? A 2-column proof is essentially just an organizational structure. It simply breaks things down in 2 columns to kind of give us some organization. On the left-hand side, we'll have whatever claim we are making based on a given amount of information, whether it be diagram or something we're told about that diagram or whatever, but we're going to make claims, okay? And you can think of it this way. If you were asked to solve for a variable, as you were moving constants away and getting the variable by itself, each of your steps would have to be justified, right? Your actual step would be the claim, and then your reasoning would be the justification for that step. Say, for instance, if you had 2x equals 15, you would divide both sides by 2 to get the x by itself. The actual division would be the claim. Your reasoning would be that as long as I am dividing the same thing to both sides, I am creating an equivalence. Basically, I'm not changing the formula. It's called the division property of equality. Okay, and so the actual act of dividing would be your claim, and then explaining that because I did it to both sides would be my reasoning as to why I could do that. And then the fact that I ultimately get x by itself would be my goal. So in this case, we were given that these 2 figures, this is a much smaller scale, you can tell, these 2 figures were parallelograms. That was pretty much all we were given. And then we were asked to prove that angle B all the way over here on the left had to match or be congruent to angle F all the way here on the right. And then we were given the following format. So here's what you will see on your assignments, what you'll see on my tests. Anytime you were given a 2-column proof, I will give you basically a fill-in-the-blank format. Most 2-column proofs, when people do them, are completely blank. They have to create them. Okay, they have to create some claim and justify that claim, make some other inference and claim, then justify that new claim, working their way down ideally to what they need to prove. In this case, what you'll be given is you'll be actually shown how many steps it will be able to take, and you'll be given one of the 2 columns for each of the entries. In this case, for the first entry, for first step, I have you create some claim, but I give you what reasoning or justification will make as to where that claim comes from. Namely here, I tell you that whatever your first claim is, it's going to be whatever is given. Okay, and I'll go through this in a minute. For entry 2, again, I make you make whatever claim is going to be inferred from that first step, but I tell you that you're going to be using, or your justification is going to be using the opposite angles theorem. For entry 3, again, you have to make the claim, but then I tell you that you're going to be using the vertical angles theorem for that claim. And then for our last step, for what we're actually going to be proving, I actually give you what your claim is. Your final claim, as with any 2-column proof, will be what it is you are trying to prove. In this case, that angle B is congruent to angle F. But now you have to come up with some reason why as to that claim is true. And I'll again go through that on our solution sheet. All right, so let me jump to our solution sheet so you can see this kind of concisely done. Cover this, make it a little less busy. There we go. All right, so again, this is our solution sheet. It's on Google Classroom. You can check this out. In blue here, you will notice the pieces that you were given in this 2-column proof, namely 3 of the reasons and then 1 of the claims, namely the last claim. And then in orange here and a little subnote there in pink, these are the pieces that you would be putting in for your answers. Now, on big ideas, the way this would look is basically you'd be given some of these pieces and you'd be filling in the blanks either with like a little like click and drag thing where there'd be a copied and pasted answer that you would just move into the correct spot, or there'd be a drop down menu where you click on one and it would give you some options and you pick the correct one. Okay, that's what you can expect for how you'll be tested and assessed on this for both homework and for my tests. So let's work through it. This one should be a freebie for everyone, this very first one, particularly on my tests. Anytime you are making an argument, doing a proof, you can only ever begin with whatever your given information is. I can't just pull information out of nowhere or make wild claims out of nowhere, despite what you might see online or on TV. Okay, I do need to just begin with whatever evidence is there, namely the diagram that I'm given and any given information about that diagram. In this case, the fact that A, B, C, D, and G, D, E, F were both parallelograms. I just copy and paste that to my first claim because that's what I was given. So all of your proofs will start the same exact way. It'll just depend on what information you were given. Just copy and paste it. Step number 2. You were asked to fill in a claim and you were told that the reason was going to be using the opposite angles theorem. That's a massive hint because that tells me exactly what pieces will be congruent to the other. Now, you won't always have congruences and stuff like that, but in this case, if I'm not sure what to do, I might want to look up, well, what does the opposite angles theorem say? It tells me that in a given parallelogram, angles that are opposite each other inside of that parallelogram are congruent to one another. And so that's where I can connect the dots, just like we did on the whiteboard, where I can say, all right, angle B has to be congruent to angle CDA on the left parallelogram, and on the right parallelogram, angle F has to be congruent to angle EDG. That's the opposite angles theorem. For entry number 3, I'm told I'm going to be using the vertical angles theorem. This was the one that's a little bit of a throwback to Math 1, where it told me that it'd be useful here to understand that for vertical angles, I'm looking for an intersection. And the only intersection that's happening here is at point D. And because of vertical angles, the ones that are going to be helpful to me are angle CDA here on the left and then angle EDG here on the right. They have to be congruent to one another. And then for my last entry, In this one, I'm actually given my claim that angle B is congruent to angle F, thus completing the proof. I have to just come up with a reason why, based on the information that I've just done, why I can immediately jump to what I need to prove. And the reason I gave was substitution. Substitution. Namely, the reason I can go from CDA and EDG being congruent to each other immediately to B and F is because B, angle B, is the same exact thing as angle CDA. So I'm just going to replace or substitute angle CDA with angle B. Angle EDG here on the right is the same exact thing as angle F. That's what I proved with the opposite angles theorem. And because they're the same exact thing, I can replace or substitute angle F in for angle EDG. And so I've just replaced both of them, and that's how I can get to my claim. Yeah, and I made a little subnote about that in that pink there. But you can see this on your solution sheet. All right, let's jump to our last two problems from the section. I'll go through these two a little bit faster. Okay, these are both coordinate grid problems. So you will be tasked with plotting points and that sort of thing. The positive here is that hopefully you're comfortable with plotting points. All right, so our first problem, we're given this situation. Find the coordinates of the intersection of the diagonals of parallelogram Lmno. And then they give us what L, M, N, and O are in coordinate form. So essentially, we're going to be tasked with this. First, obviously, plot your points. You will create a parallelogram. For the record, in case you didn't know, this symbol right here is the symbol for parallelogram. It looks like a little sideways parallelogram. I know it's a little sloppy in my notes, but you'll see something like this where it's like parallelogram LMNO. Okay, so it'll be like a little sideways looking rectangle right there, a little angled rectangle. Anyway, that will mean parallelogram. And why does that matter? Because parallelogram means all those theorems immediately apply to this guy. But they're asking me to look at the intersection of the diagonals. So let me jump to my solution sheet so you can kind of see this finalized, so you don't see me having to struggle through actually plotting this on a coordinate grid and all that good stuff. Okay, so here is that last problem. It's a little less busy. There you go. All right, so after plotting L, M, N, and O, we get the following points. You can see it as a parallelogram. And they're asking us about the intersection of the diagonals. Okay, so once you connect your dots and you get this parallelogram shape, it would also be a good thing to draw your diagonals. You don't always have to draw diagonals for a parallelogram, but since it's asking us about an intersection of diagonals, it's going to help us to draw. So drawing our diagonals, we're looking for where they cross. Now, here is where you need to be very careful, because it's very tempting for a lot of high school students to, at this point, just be like, eyeball it, guess it, approximate it. Okay, it looks like about 3.5 and 2. You would be correct in this instance, but be careful with the decimal points. Not everything will be as friendly as this one. Okay, I do it to kind of make it a little bit neater on our page and stuff, but if it is anything other than like a half, where most of us can kind of eyeball a half, but if it's like a third or a quarter or something like that, it's a lot more difficult to estimate that. And you'll get wrong answers unless you're actually using, in this case, the midpoint formula. So why, let me get to why we're going to be using the midpoint formula. So the fact that we are dealing with the parallelogram, as I've said a couple of times now, that means automatically those 4 theorems will be applied here. One of those theorems has to do with the diagonals. The Diagonals Theorem tells us that the diagonals of a parallelogram have to bisect one another, meaning they chop each other in half. Okay, so there's a long way about trying to find this intersection, particularly if it's a little less convenient to round or eyeball. And that would involve figuring out what the equation of this diagonal line is, and then the equation of that diagonal line, and using system of equations to set the equations equal to each other to solve for the variables and ultimately find out what the coordinate point is, the shared coordinate point. Well, that's a lot of work. It's possible, it would work, but it would take a long time. So how can I use something a little bit simpler? And the hint here had to do with the fact that it is a parallelogram. The fact that it's a parallelogram means that these diagonals cut each other in half. That's useful because now I can use midpoint formula. For either of these diagonal segments, either OM or for LN, if I find the midpoint of that respective segment, I will have found the intersection. So it doesn't matter which diagonal you use. I'll use OM, O being at 0, 0, M being at 7, 4. And so what I can do is I can find the midpoint between those two. And if you don't remember what the midpoint formula is, I'll go ahead and write it really quickly here. X1 plus X2 over 2, and then Y1 plus Y2 over 2. This tends to intimidate students, but essentially it just breaks down like this. You're finding an average X value and finding an average Y value. So here, if I'm talking about the X values, the X value for O is 0, the X value for M is 7. 0 plus 7 divided by 2 would give me 3.5. For the Y value of O is 0. The Y value for M is 4. 0 plus 4 divided by 2 gives me 2. There's my midpoint. Okay. Finding an average of something is adding up a bunch of objects and dividing by the number of objects. You're doing that just with 2 separate coordinate points. Okay. So when you get questions like that about the diagonals, you can use the midpoint formula. All right. Last problem. Again, let me jump to our whiteboard, or sorry, jump to our notes. All right, this last problem right here, we are given 3 vertices or 3 corners of a parallelogram WXYZ, and they tell us what W, X, and Z are. Our job here is to find the missing 4th corner that will be positioned in some way so that we have created a parallelogram. So we are given 3 corners of a parallelogram. We need to find a 4th corner so that it really does make a parallelogram and it's not randomly placed, so it's some other weird 4-sided shape. All right, so let me jump to the solutions one last time. Here is that problem. So the obvious thing to start with would be to plot the points that they give us. They give us W, X, and Z as shown here. Hopefully, again, you are comfortable plotting those points because that will be critical for figuring out where the 4th one goes. And the tricky part with this problem and why it's important to make sure that you're plotting these points first is based on their positioning, you'll see that it makes this kind of wedge shape once I connect the 3 points together. And when I've made this wedge shape, I know that's going to have a 4th corner somewhere, right? I'm not making a triangle for the record. I am going to make a 4-sided figure. So based on how the wedge shape opens up, I know my 4th point has to be somewhere inside that wedge. Okay. If you were to try putting that 4th point anywhere else outside the wedge, you'll end up with a very weird looking 4-sided figure. Okay. So I know it has to go up in here. So what I'm going to actually use here is breaking down parallelogram into its root of its word, namely parallel. When I'm talking about things being parallel, particularly on a coordinate grid, I'm talking about things having equal slope or equal rise over run. And I kind of break that down over here in these notes on the solution. Okay. But another way to think about it is this. Here are the 3 corners that I have. I need to find my mystery point somewhere in here that makes it a parallelogram. Quick way to do that, looking at W to here, how I get from W to X, this is going to have a slope, this little line segment right here. And that slope has to match whatever slope is going to be over here for this side. So this slope here, if I just count the squares to get from W to X, it should be the same exact mapped from Z to Y. So W here to X, I would go left 2, up 5. So from Z, I should follow that same exact path. Left 2, up 5. And that matters because I've just created 2 equal slopes, and that means it will be parallel. I could also have done from W to Z, so wedge point to Z, down 1, right 5, and then I would go from X, and I should be able to find Y the same way, down 1, right 5. Again, that's just kind of the quick way to do it on graph paper, or especially on big ideas. You will be provided a coordinate grid, and you can kind of just mess around with that, or Desmos.com also has those things available to you. But that's how you could use slope and the idea that equal slope means parallel to quickly solve this problem without having to do any real computation in that case. But that concludes section 2 notes on properties of parallelograms. I'll go ahead and stop recording now.